Welcome back to another HVAC-Engineering-Techie channel video. This is the channel where we talk all things HVAC, engineering design, construction, equipment, systems, test and balance extensively, controls, efficiency, and system performance. These videos are intended to be educational in nature to help you in your career and, of course, on the job. Today's lesson is on hydronic balancing of variable flow chill water systems. This is another in the series of how to actually balance a system rather than just components. So hopefully this will be helpful to you. Please, I'm really begging you, become a subscriber. It really helps me and I really appreciate it. Costs you nothing. It's absolutely free. It's painless for you. Just simply click the subscribe button, the black button down below. Give me a thumbs up if you like the video. It helps me because Google uses that data to evaluate the video, and that helps me. That'll help me stay on the air. So thank you in advance for doing that if you're not already a member. So let's go ahead and get started on talking about variable flow chill water balance. Okay, so the first thing you always do on a job whenever you get there is you have to do a pre-balance design review. To fully understand how to balance a system, you must review the design. These are the things you normally look for when you do design. Do the flow of components match? And this is kind of important. The chiller evaporator flow to the primary flow, those need to match. So the primary pumps, of course, are the ones that pump through the chiller, and the secondary pumps are the ones that pump out to the field. Now this is just saying chiller evaporator flow, that the pumps can pump enough for the evaporator, and that's really important. The condenser flow matches the condenser pump. Total flow of all connected coils to primary or secondary pump. The reason is there's two different kinds of variable flow, so you have to make sure you have diversity. And if you add up all the coils and that GPM is more than the chiller or the pump, then you have diversity and you have to deal with that. Verify the condenser pump has sufficient net suction head for the piping arrangement. So remember that all pumps have to have a certain amount of pressure on their suction to perform correctly. And so you have to check that. Normally it's okay. The only place that's really a problem is on cooling tower suction pumps. It should never be a problem in a closed system. Review the design of system effect issues, which are issues that increase the system pressure more than just the pipe friction. So that could be fittings like bullhead T fittings. It could be wrong size pipe. It could be if piping velocity increases down the pipe system. Normally pipe systems start off at high velocity for bigger pipe, and the velocity gets less and less as you get smaller and smaller the pipe. That's to keep the head contingent. And remember, system effect is where we require to increase the velocity of the water, and that takes horsepower. So we want to do that. You can go from high velocity to low velocity for free. It does that by itself, but you can't do the other way around without using horsepower. Now this is a field review. The first line is wrong there, but basically now when you done your design review, you're familiar with the drawings, you go to the site and you inspect the site. So do the flows and pressures of pumps and equipment match the design? So basically, is the equipment installed the same equipment that designed? Do the pumps they actually install have the same GPM as the design? You kind of check all that out, make sure something has changed. It's not unusual for general contractors or mechanical contractors to forget to send you addenda. Really, really irritating because they'll make changes and not tell you about it. So have all pipe strainers been blown down and verified clean? So the large system pipe strainers normally have a sieve with large holes in it that are slightly smaller than the holes in the volute of the pump to keep from anything clogging the pump. Inside of that is a fine screen sieve. That's called a startup strainer. So what that's designed to do is to catch all the weld slag or anything that's in the pipe that shouldn't be there. And that's intended to be taken out and removed after they clean the system, started it up, and that's be taken out before you test and balance. So you may need to ask the question, did you remove the sieves? If you get a strange response, then maybe you ought to ask, let's take one apart and find out what's in there. And if it has a startup screen, they have to remove them all. Is the system totally full of water and makeup water set at the correct pressure? This is the Achilles heel of a water system. It must not have any air in the system. Plug flow or total bubble flow will affect your balance drastically. So you need to make sure it's full of water. Is the makeup water system installed at the correct location? Where do they have the makeup water? It needs to be to the suction of the pumps. If it's not near the suction of the pumps, then your system will not work correctly. Are pump pressure measurement gauges or ports installed correctly? This is the one that we find wrong about 50% of the time on jobs. No matter what the design says, a lot of times these will be installed in the wrong location. The pump, for us to read a pump curve, we need to know the inlet pressure at the exact inlet of the pump and the outlet pressure at the exact outlet of the pump. It can't be 20 feet down the pipe or on the other side of the check valve or on the other side of the strainer. That won't allow us to read the pump, so you have to make sure those are in the right location. Inspect the decoupler pipe on the variable flow system for correct installation location. Now, we'll talk about the decoupler, but if the decoupler is installed in the wrong place, the system will not flow the right amount of water. And we find these installed wrong about 30% of the time. Review pipe installation for bullhead tees. Should never be a bullhead tee on the job. A bullhead tee is a pipe that has water flow from going into the side lateral of a T and going both ways, left and right of the T. That's a bullhead T. Or even worse, if you have water flowing from the left and the right, crashing together and then expected that both those streams to combine and go out the side outlet of the T, that's a bullhead T. And the reason we don't like bullhead T's, if you change a flow, so you have a bullhead T and you've balanced it and you got a certain amount of water going right, a certain amount of water going left, and something comes on, it goes off, that changes the flow, the head changes drastically. The pressure drop of that T changes drastically. Can be up to 200%. And that's what makes central plants with multiple pieces of equipment sometimes function erratically because they have bullhead T's. Review the installation for system effect issues. Increase in water velocity down the pipe, same thing we did for the design. We want to make sure they haven't done something, because remember, the drawings are somewhat dogmatic in nature, and a contractor may not actually install the system exactly like it looks on the drawing. There's nothing wrong with that. It just makes sure they don't have any issues that's not going to allow the system to be functional. This is a variable flow primary secondary pump chill water system, and this consists of a condenser side of the chiller and an evaporator side of the chiller. And we have condenser pumps. We have two, one primary and one standby. We have primary pumps, one primary, one standby. Then we have secondary pumps, which we have a lead pump and a lag pump. Same as these other pumps. So on the condenser side, the pump actually sucks from the tower basin, takes the water, puts it through the chiller where it gains heat, puts it up over the tower to relieve the system of the heat. Now you'll notice that this system has a bypass from the returning water to the basin, and that's a cold weather bypass. That's intended to keep the water from getting too cold. If it gets too cold outside, it bypasses it direct to the tower. Now, sometimes you'll see the designer to take this pipe and pipe it right down in here instead of into the basin, and that's a mistake. That's an incorrect piping design, and the reason is because the pressure drop when it goes back into the tower, if you dump this water in the tower basin, you haven't disrupted the pressure drop of the system. It's exactly the same as if it was going over the top. If you pipe it right down here, when it's in bypass, this is now a closed piping system, and you have the pressure of the pump. What pressure is in this pipe now is in the suction of the pump. So this sees a whole different pressure profile than when it's going over the tower. It's going over the tower. This goes back to atmospheric pressure into the basin. It's now an open system. So that piping design is absolutely incorrect. Now, will it work? Sure, it'll work, but you will never be able to balance between the two. So in other words, when you're in bypass, this whole system will see a different pressure profile, and you can't change it because you can't have both. You can only have one. So this is a system you can't balance. Is it terribly critical? No, it's just not right. So, I mean, for the system to work best, it should be into the basin. Okay, on the evaporator side, so we have the field, the coils, the loads, and you notice these loads have two-way valves on them, and they're designed to variable flow. So this coil can have from 0 flow to 100% flow, as all of them can. Now, sometimes sometimes on a job you'll see a three-way on the last coil up here, and that's intended to keep the mains mixed. So if we have a way off a design day where there's not much load, and we don't, so then we're not starving these secondary pumps for flow. So we put a bypass. We'll either put a bypass valve here and let it modulate on pressure, or else we'll put a three-way valve here, so we get at least one coil to keep it keeps the lines temperature where they should be, and it keeps some flow. Okay, so here, let's go through the flow path. So here we have a pump. It's getting water from the chiller. Cold water from the chiller goes through the suction of the primary pumps, a solid separator, and it goes into the suction of the secondary pumps, and the secondary pumps pump out to the load, and the load comes back to the chiller. So that's how primary secondary works. Now, the reason it's variable flow, remember, this is a constant flow system, and this is a variable flow system. So these pumps can pump this water around like this, and if this has a bunch more water than this, then the water comes back down, and some of it goes through the decoupler in this direction, and this can run around like this. Okay, so it's possible for these pumps to actually have absolutely no flow, and this to actually operate that way. Now let's go the opposite. It is possible too, if this is a very low load, or no load, which you'll never see, but very, very low load, then these pumps can pump this way through the decoupler and can keep this flow going. So these are two different flow loops that are completely independent of each other. This is the decoupler. This is the problem child. This flows in two different directions. You notice when the primary has more water, it flows in this direction. When the secondary has more water, it flows in this direction. And that is the secret to not have it wrong. A lot of times, if you have it where instead of this one into the suction of this one, they're both sucking off the return, then the water always goes the same direction to the decoupler. It means it has twice the flow to the decoupler, and it can't do that. So that's why you have a chiller restriction on those jobs. So now, why would they ever install it that way? Well, it turns out, so the decoupler should be full pipe size. It should not be a reduced decoupler, which you see sometimes, which can be okay. But what happens is in your drawings, it's a diagram drawing, and you see this decoupler on the diagram, which looks real simple. It looks like it's in the right place and everything. But if you actually get out to the field and you look at this pipe, boy, this pipe is like spaghetti out there. It doesn't look anything like it does in this diagram. That's where we get into trouble. And sometimes the decoupler is a vertical pipe, not a nice horizontal pipe like on the drawings. So basically, we should pay attention to that. This is as I said, the primary, and this is the secondary pump system. Now, the expansion tank has on it here supply water, so it has a backflow preventer and a pressure reducing valve. This comes over to the suction of the pumps, and it really should be the suction of the secondary pumps is where it's designed to be, okay? So what happens is that when the system is off, this provides enough water pressure to push the water clear to the top of the pipe. If this is not set high enough, then when it's off, the water will seek a level down here somewhere, and this will be a vacuum, under vacuum, and will actually pull air out of the water to fill this with air. And when that happens, then when it restarts, the water comes up here, it's pushing a slug of air through the system, and it will probably mean plug flow. So this is why systems don't work well. And in the worst case, it can airlock a coil or airlock part of a piping system. So this is why we check, as a balance guy, you always need to check this pressure to make sure it's right. And of course, you take the height from here all the way to here and add a few feet, divide by 2.31, and that's the minimum setting PSI that this could be. So that's really important to do. Now, the controls for the system, we'll talk about that in a minute. We have starters on the pumps, starters on these pumps, and these are not variable flow. These are constant flow. And then we have VFDs over on these pumps because they have to speed up and slow down for these coils. And we normally have a VFD on the tower fan. It's a no-brainer to have a VFD on a tower fan. The energy saved will pay for itself up in less than 18 months on every one I've ever calculated, and I have calculated a lot of them. So I just give up and say every tower should have a VFD. Remember that not only does it save energy, but it also saves gearboxes if it has a gearbox, or it'll save fan belts if it has belts on it. So those are really important to do. Other thing that's important here is the controls has a differential pressure sensor on this pipe. It should be located about 2/3 down the pipe. There are some companies out there that like to put it right here in the central plant, and that's not recommended. The reason is because it doesn't have the same range of measurement as up here. Up here it'll be fairly low pressure, low differential, and up here it'll be high pressure. And the instrument only has so many steps. I think it has like 1,000 steps. You may think, well, that's plenty, and it might be. But up here, there'll be larger units, so that we have a lot finer control if we have it down here. And now remember, this is a closed piping system, so if you have a pressure differential here, you'll have a different pressure differential here, but it'll be similar. In other words, if this goes up, this goes up. The only difference is that the pressure is higher in these pipes here. So, and then many times you'll have more than one. If you have different piping systems running around, then about 2 or 3 of them, they'll low select to do the pressure readings from there. That's about the only thing that's really, this temperature sensor does the tower fan and bypass valve. This temperature sensor does the chiller. Okay, how do you control these? Now we're going to go through a sequence. This is a simplified sequence just to tell how the system operates. You wouldn't use this to program a system. It needs to be a little more complicated than this one. Okay, the system should be enabled based upon an occupancy schedule. Start the lead condenser pump, lead primary pump, and lead secondary pump. After confirmation of flow, enable the chiller. After 5 minutes, any lead pump fails, then do an alarm and start the lag pump. Chill water supply temperature set point should be 44 degrees. Chill water supply temp should be reset based upon cooling coil valve position. Reset the range shall be from 42 to 50 degrees. So we'll actually look at where all these valves are. Now, some people used to use outside air temperature to reset this, which is an open control loop, and you shouldn't do that. You should reset it from your load, because you don't know, it might be an internal load, not an external load that's needed. Okay, so now we've done the chill water set point. Secondary pumps to be modified to maintain differential pressure set point of 15 psi, plus or minus, because you as a balance person is going to establish what that correct differential pressure set point should be and have that programmed into the system. The condenser water temperature set point should be 85 degrees. Modulate the fan speed to maintain temperature set point. Reset that temperature based upon ambient wet bulb plus 10 degrees between 65 and 85. Modulate the tower bypass valve to maintain a minimum chill water supply temperature of 65 degrees. Well, the reason we're doing all this with this 10 degrees above wet bulb is we have found that a chiller is much more efficient with lower lift. So the chiller it has to actually take and cool the water, but the higher the water temperature entering the chiller, then the higher the lift it has to its temperature. So if you can get this water colder entering the chiller, then you're going to have lower the lifts. But there is a limit. Chillers can't take infinite cold water, right? So normally it's about 70 degrees. Some of them are 65 degrees. It depends on the manufacturer. But what we want to do is we're going to drive this water down as cold as the chiller will take, so it'll be as efficient as possible. Now, we've seen a couple of large studies done on whether that's more efficient than not, because remember, when you lower this temperature of the tower, this fan runs more. But the tower fan, you know, for a 350 ton chiller, it might be a 50 horsepower fan motor. Basically, running this up on the VFD for more time is nothing near what the chiller will save. So basically, running this down is good. And we're using 10 degrees. That may be adjustable. You may want to go colder than that. But the reason we're using 10 degrees is basically I live in a dry climate, whereas I have very low wet bulbs, and I don't want to get that cold, so we keep the 10 degrees. So basically it depends on where you're living, where the system is at. If the chill water supply or chill condenser water temperature rise more than 3 degrees above set point, send a trouble alarm. There'd be a timer in there normally, but don't put that in. Monitor the chill water supply, chill water return, condenser water supply, condenser water return, temps and outside air temp, and humidity. All right, so now let's go on to what you really want to know. How do we balance the system? Test the pump's chiller cooling tower operability. Verify units provide flow and correct temperature. So before you balance this, it is possible for you to balance the water flows to the coils without the chiller being able to run, but don't do it. You need to have temperature so you don't ever have to come back if you have to check a temperature. And you need to be able to clean it. So it needs to be able to run, and the controls need to be ready to run. Verify all coil balance and control valves are 100% open. So now on all the coils, you've got a control valve and you've got a balance valve. You need to command open the control valves, command them open to 100%, and leave them there, lock them there. And then the balance valves, you need to manually check that they're all 100% open. Just like an air system, same problem. Gotta make sure they're open. Balance the secondary pumps to slightly overflow, 5 to 10% overflow. Primary pumps and condenser pumps to design flow. Measure the shutoff head and total flow head. Record all pump voltages, amp speed, and pressure, outlet pressure, and total flow. So once you've got that, now if the system has diversity, so you've added up all the valves, and if it has diversity, then you're going to close some of these valves around the system to make sure that your field flow matches the secondary pump flow. So what you're trying to do, since it's a variable volume system, you're trying to take a block of water from the pumps, and you want to balance that same exact block of flow in the coils. You don't want them different, you want them the same. So the way we do that is, so you're going to go balance, you're going to find some valves to go close out here in the field, and you want them to be slightly less water, slightly. I mean, like if you pick 20 coils out here and say if you needed 500 GPM, you have 500 GPM on the pump, and you have two choices. You can, if you close one, your GPM is going to be 480, and if you don't close the other, it's going to be 520. Pick the 480. You want just a few less GPM, so as you balance back and run up the head pressure, you still have enough water. Now, you can't do too much or else it defeats the way you're supposed to balance. But trying to balance with not enough water is somewhat complicated. So, it helps if you have smaller coils so you can trim that load and get fairly close. It is best practice to spread these closed coils around the system. Don't put them all in one spot. So now that you've got your diversity set up and we're ready to start, you pre-read all the balance valve flows with all the valves 100% open to diversity. So you run out there and you just read the coils. Don't balance anything, just read them. If you're using a series balance, there's two methods we're going to talk about. One is series, which means you just go balance the valves. Or you can proportional balance like you would a proportional air balance. You can do that. So if you're using a series balance method, start at the coil with the highest flow and adjust balance valves for correct coil flow. Move on to the next highest flow valve and continue to all coils are balanced. If you're using the proportional balance method, then start at the coil with the lowest flow and balance each valve proportionally to the previous balance valve and continue to all coils are balanced. See our video T7 for proportional balance. Some more exact details on that. What's the details in this? I mean, when you're starting out here, if you're using a series balance method and you're starting at the highest valve, you got to kind of look at the valves. If that's a very big valve, then you can balance it down and watch what happens. Now, in both of these situations, both series and proportional, you will have a target valve, and it will always be the valve with the lowest percentage flow. And that's your target valve, and it will be so that you don't balance that valve. You don't touch that valve at all, and because you're going to balance and push water to that as you go. So if you're using a series balance, this is kind of a hunt and peck method. It doesn't actually proportional balance, but it does balance, and both of these series works. But when you start with series, the first two valves I would balance down below design a little bit, because as you balance the others down, it's going to push that water back up. So you want to keep balancing down, and you got to kind of get a feel for how and over time you'll get used to how to do this. And as you keep getting down, you can keep looking at your target valve to see where it's at as you keep going. And when you get about halfway down, and if you have small valves, you can just balance those down to design flow. You don't need to go down a little bit more. And then when you get close, you have to kind of look at where the valves are. If you have big valves left near the end, then you'll have a lot of opportunity to push that water right to that valve. But if you have only small valves left, you don't have a lot of opportunity because a small valve doesn't push a lot of water downstream. So you got to kind of think about that as you go, or else you're going to have to go back and rebalance a couple of times to get them correct. And that's what a lot of guys do. They will just, randomly set those down and watch what they're doing and get a good feel. And then if the target valve doesn't work, then they have to go back and trim some more back to get it. And that's common. It's not unusual to have to do that at least twice, maybe even 3 times on the system to get that. But normally you can balance down, because you're trying to get the target valve up above 90%, and you're trying to get the big valves down below 110%. That's what you're trying to do. So you've got some leeway there, and you get through that, but you can't do it. Now, proportional balance, of course, you start with the 2 lowest. So you got the target valve first, and you leave it open, and you go to the second valve, and you balance it down so the 2 percentages are exactly the same. Then you go to the next one, and you balance it down so that those 2 are exactly the same. Now, remember, as you go, when you get to a valve, and you notice the last valve was at 78%, and you start balancing this one down to 78%, that existing valve is no longer 78%. It may now be 79%. Well, you're trying to get it to its current position with this one balanced. So you have to go back and forth just a little bit with those 2 valves till you get them near the same. Then you go to the next one and do the same thing. Well, what the beauty of the proportional balance is, you don't ever have to go back. You know what I mean? As you work your way around, you might have to, if you don't get to the water you want, you may have to go to a couple of the bigger valves and get them down a little bit more to push a little bit more water to that valve. But proportional is actually, gets to be easier if you have a whole lot of valves. If you only have a few valves, series, you can almost do series in your head if you have a few valves, but if you have a whole bunch of valves, series gets to be really complicated. So proportional is probably the preferred method. I'm not sure a lot of guys use proportional method, but in both of the cases, you have to run back and forth a little bit. In proportional, you're running between the 2 valves you're doing. In series, you're running between all the valves as you get back and forth, so that's why proportional is better. And then we also have a session T-20 is on diversity balance, both for air and water, and it'll explain those to you. With the secondary pumps, okay, now this is really kind of important. A lot of guys balance systems by leaving the control system in charge of the system pressure, and you should not do that. You should just ignore the system pressure, right? Make sure that's not operating. And what happens is you basically lock the coils open, and you have the secondary pumps locked at flow. By locked at flow, I mean you've gone to the VFDs and you've manually set the speed. You don't let the system, you keep it in manual mode so the system can't control it, and you set it to speed for design flow. And normally I pick design flow from the pump curve, so we set up the VFD, and so it's flowing design flow. And then you got all the coils to match that diversity locked in the field, and you've gone out and balanced them. Now that they're all balanced, and if they're slightly low, so let's say you've backed up enough pressure that your system's slightly low, then you go back to the secondary pump, and you'll notice that its flow has changed because it's ridden back up on the curve. So now you inch it up until you got design flow again. Now you know you got design flow in the pump. Now you know you got design flow in the field because they're all balanced. So what you do then is you read the differential pressure on the system, and that is your set point, and that's how you get the set point. I've seen some guys try to guess at what it is, and we ran out of water, so we guess again, then we run out of water and we guess again, trying to keep that automatic control operating. But the problem with the automatic control is you're balancing down, you're changing the pressure, and what's happening is the VFD is trying to keep that pressure so it's modulating well. But remember, we're trying to do a block of flow to a block of flow. The right way is to not have it modulating, and when you're done with the balance, now you know exactly what the set point is because you've got the pumps blocked and you got the coils blocked, and they match flow. It's perfect. That's the PSI you want to maintain. Okay, so release all controls to automatic operation. Please don't forget to do that. It's a little embarrassing when you forget to do that. Balance water flow over the cooling tower fill. Yeah, so it is all totally wetted. Okay, on the fill, when you balance the water over the top of the cooling tower, you'll notice that the pans up there, or else there might be flow nozzles, whichever, and you're equalizing the flow all around the tower so that it wets the fill evenly. What happens if you allow it to splash, water to splash onto the fill, and then it wets and dries, it builds scale very, very quickly, and it will scale a tower really seriously. So we need to have enough water, and that's why a designer should never have two chillers on one tower where the flow changes. So he has, say if you have two chillers that have 200 GPM each of condenser flow, and you have one on and it puts 200 GPM, you turn to it has 400 GPM, that won't work because it'll scale the tower seriously. So we want it wetted entirely. If it's off, it can dry, that's not a problem. But when it splashes, it wet dries 100 times a day, and that's not a good thing. So we don't do that. Okay, so after you've done that, adjust the cooling tower water level if required. You are going to have to set this level, and you have to set this level so that any water coming, when you turn the tower off, the water that drains back to the tower doesn't overfill the basin. This is really a big problem on multiple tower systems. They're uncommon basins. We have to balance these. It's your job to balance between them so that doesn't happen. So we don't overflow and then fill, overflow and fill, because it's just a waste of water, and it causes problem for operations. Verify flow and pressure drop across the chiller, evaporator, condenser. Record final flow and in and out temperature. Another thing, record final pump flows and operating pressure. Record makeup pressure set point, what the set point for this makeup water is. And also, more than likely, you're going to have to come out early on the job and set the water through the bundles, because the chiller manufacturer won't start this chiller until he's guaranteed he's got design flow through those. So you may have to set this pump, primary pumps and condenser water pumps, to get that to let him start up before you balance. So that's a primary, secondary. It's not difficult to do. It's easy to do. Critical factors are no air in the pipe, and that the decoupler is actually done correctly. Okay, so this is a variable flow chiller. Now, it's different than the other one in that it doesn't have primary, secondary pumps. It actually has a variable flow chiller. Now, chillers aren't designed to be variable flow. They can be, but a variable flow chiller actually has a flow meter built inside of it, and it has controls to the compressor to vary the refrigerant so it never freezes up a chiller bundle. So basically they have a special feature on them. They're not just a regular chiller done that. So what's different about this system is, of course, the condenser side is exactly the same, but the evaporator side, the pumps, which we call them primary pumps now, they suck from the chiller and take the water and run it out to the coils, and it comes back to the chiller. But the problem is the chiller, even though it's a variable flow chiller, it can't do below 50% flow. So you have a bypass running so that if this load gets less than 50%, it opens up and starts flowing. It modulates open and starts flowing more water to the chillers, so it never gets below 50%. So originally, we tried to control these valves, this valve under pressure with chiller pressure. Doesn't work at all. Please don't let them do that. The best way is with a flow meter. I put a flow meter in this pipe, and that flow meter will control this valve directly, and those work great. That works fine. Doing pressures is a headache. It just can't seem to get it to work. And once you get it to work, something changes. I mean, a blip of air in the chiller bundle will drive the pressure sensor crazy, or else a little scaling in the chiller bundle drives it all crazy. So you really need a flow meter to run those. That's a design issue, but one we found. And again, these are two-way valves for variable flow. And again, this one might be a three-way, or they may have an automatic valve to bypass them, or even sometimes a 3/4 inch valve, just manual valve open between them for that minimum flow. A typical control sequence is, again, it's all enabled based upon occupancy. So start the pumps first. Once you got flow, enable the chiller. Remember, the chiller has its own controls. You're just enabling it, or maybe done a reset to it. If after 5 minutes any pump fails, send an alarm, start the lag pump. The chill water supply temperature set point should be 44, and you'll reset it based on valve position, just like the last system. No difference. Primary pump speed should be modulated to maintain a differential pressure or 15 psi. But remember, you're going to set that later on. The chill water supply flow meter shall modulate the bypass valve to maintain a minimum of 50% evaporator flow. Chill water supply temperature set point should be 85 degrees, modulated by fan speed, and then reset it from wet bulb plus 10% from between 65 and 85, just like the last system, depending on the type of chiller. Monitor the temperature sensors. If the chill water supply temperature or the condenser water temperature rises more than 3 degrees above set points, in a trouble alarm. Monitor the chill water supply, chill water return, condenser water supply, condenser water return temperatures, and outside air temp and humidity. Pretty simple control, and the really thing about these is that bypass flow. All right, so let's look at balance. Again, test the pumps and chiller cooling tower operability. Verify unit provides flow and correct temperature. Verify all balance and control valves are 100% open, just like you did the last time. Balance the primary pumps to plus 5 to 10% and condenser pumps to design flow. Measure the shutoff head and total flow head. Record all pump voltage, amp, speed, and pressure, outlet pressure, and total flow. You'll probably remeasure the primary pumps once you've balanced them. If the system has diversity, close enough balance valves to the total flow equals 100% of the primary pump flow. So again, we're taking a block of water from the primary pumps and want to measure exactly that same block of water in the field. So to do that, we set the pumps on the VFD, manually set them up to flow where the pump curve says this is the right GPM. And then we're going to command all the control valves 100% open. And then we're going to make sure all the balance valves are 100% open. So once you've pre-read everything, now we're ready to actually do the balancing. And again, we do exactly the same thing we did the last time. If we use a series balance, we're going to start from the highest valve to the lowest valve. We're going to balance them down as we go to push water to the target valve, which is the one that's the lowest flow. If we use proportional balance, we're going to do it exactly opposite. We're going to do from the lowest valve to the highest valve, proportionally balancing the two valves together, the next two, the next two, the next two, until we get done and pushing water. Now, if we have to, we'll retrim the pumps to get a little more flow if we've backed it up on the curve. And at this point, once you've balanced them, you're all happy with the balance of the field, you've rechecked the pumps, and you've sped them up if they need to be speeded up just a little bit to match a flow, and you've got the block of flow from the pumps matching the block of flow from the open valves. Then read the differential pressure set point, and that is your set point. If you read the pressure, that becomes a set point of the system. And at this point, you can return everything. That also, if you got diversity set, now you need to open the valves you close and close some others to match and rebalance those. Remember, you're always balancing for that same block of flow from the pumps to the field, and you just open and close valves to make sure that happens. Balance the water flow over the cooling tower, the same thing. You need to make sure the fill is wetted by adjusting these pan out there, and you need to set the water basin just like we did on the last one. Adjust the cooling tower basin for water level. Calibrate the chiller flow meter. Now this is a little bit different because you now need to calibrate this flow meter. And there's several ways to do it. The best is time flight flow meter, clamp-on meter. That's the best because it's a very accurate meter. If you don't have one of those, when this chiller's brand new, you can check the differential pressure on the chiller bundle and calibrate it that way. It's not as accurate as a time flight meter, but that's whatever you do, you got to calibrate that meter. Release the control to automatic operation again. Verify flow and pressure drop across the chiller and the evaporator condenser. Record the final flow, in and out temperatures. Record the final pump flows and operating pressure. Record makeup water pressure set point. So again, just like that, this is a little simpler system to balance. Only thing it gets a little more complicated if you have more than one chiller. Then you have to see what the design is. Where the design was set up to try to maintain two chillers, it should be one per chiller. It makes it much easier. But multiple chillers are more difficult on this system. On the last system, it doesn't make any difference. They're the same. Okay, the next type of variable flows is campus flow systems, where you have a lot of buildings. And we have one big pipe system out here to run around. We have primary pumps or secondary pumps, whatever these are. This is part of a central plant. And the central plant is just like either central plant we've talked about before. And these pump water around to different buildings. and they have VFDs that run off differential pressure. Same thing as a regular building, except these are big components. So this is a variable primary campus system. So the variable primary campus system, the sequence is super simple. It's building air handler and control sequences are the same as for any other air handler coil control sequence. So these are the same. These are balanced separately. If these were all brand new buildings, this is a very simple flow system. So it's got campus systems and it's got a balance valve. So you're going to set the total flow to the building is all you're doing. And other than that, this acts like one huge building. By the way, there aren't many of these. They normally will be the next ones we look at. The central plant control system is the same as any other central plant. The primary secondary pumps, P1 is the lead pump, P2 is a slag or standby pump. The lead pump VFD shall modulate the pump speed to maintain the differential set point. If the differential pressure drops more than 2 psi below the set point for 15 minutes, switch to the lag pump. Now, these are normally really big pumps, so it's a little bit different. The primary and secondary systems temperature set point should be reset based upon the air handler control's valve position. So this one, you would probably have a reset sequence in the building saying, I need colder water, and it would send a request to the central plant to get colder water. Test and balance procedures for the central plant are the same as for any other central plant. Nothing different there. The balance flow for each building, you must set up each building for a diversity flow, if any. So now here's the problem. Say that you look out here and you add up all these buildings and you realize you got a 80% diversity flow. Well, now you've got to find a building and balance it down, take a valve and close it off to where you get diversity flow, and then go set the rest of these valves so each building has it. So in other words, you got to do the same thing as the other big, except you won't be able to close off a building because it doesn't have that. So you're not going to have a whole building equal diversity flow. So now the one problem with a system like this is you're going to be screwing up every building as you go. So normally when you see a system, these are existing buildings. So this is a new building. So you have to try to get balanced flow to this without screwing up these buildings. And it's almost impossible to do because you need these valves all open. You need these valves open to be able to do the flow, which means you got to screw up every building. So that's why you don't see many systems like this. To balance the flow to each building, you must set up each building for its diversity flow, if any. So if this system has diversity, it has to be set up. So you have to go in there and close some valves and open the others. So just pretend this is one huge building, and that's what you have to do. When you set up the campus system for total flow diversity, if any, by blocking, that's what we said before. So each building set up, and then you'll do a total one flow. Once done, open the block balance valve and block another building. So you're doing just like you would any other system, except these are total buildings. So let's go look at a more complicated one. Okay, here's a campus system with tertiary valves. So this basically has a valve that's modulating flow to differential pressure within the building. Still has a balance valve, but it's got a valve in there that's modulating flow. So this is just like a full building control, but it doesn't have a pump. Pumps are up here. So this has some problems and it has to deal with. Other than that, it's the same system, and we'll go talk about the control sequence. All right, so again, these systems in here are balanced just like any other system. This system up here is balanced just like any other system, so we don't have to go through that. Now the next one, the primary secondary pumps are run off this DP, so that can run those pumps and then set the lag pump when it's needed. So we got that, and normally these systems are around 20 psi or so, but might be more. If the primary secondary pump system differential pressure drops more than 2 psi, then we're going to send an alarm and do the lag pump, just like the other one. Each building differential pressure sensor shall modulate the building control valve to maintain the building differential pressure set point. Send a low pressure signal to the primary pumping system to increase the main pressure when pressure drops below set point. So if this pressure isn't enough in these buildings, they're going to need to send a signal up here and say, hey, I need more pressure, and then it's going to have to up. What it'll do is it'll reset the main differential pressure set point. And then, of course, the primary system set point should be temperature set point shall be based upon each building's main control valve position. So if we're flowing more water to a building, it tells us that that building could use colder water. And it's more complicated sequence, but that's basically what it does. So that way we're able to control flow and pressure to the system. Okay, so test and balance procedure for the central plant are the same. So now we're going to lock all building automatic pressure control valves to full open. We're going to do just like this with an air handler, like this one big air handler. We're going to lock that coil to design flow, and if it has diversity, then we're going to have to close off part of this for diversity so that we know what that valve has, the diversity flow. Or we might balance this valve down to diversity flow and do all these to diversity flow, so now we can do the flow of all the buildings. To balance the flow to each building, you must set up each building for its diversity flow, if any. Then you set up the campus system for total flow diversity, if any, by blocking the associated percentage flow to one building, then balancing each building's flow by adjusting the building balance valve. So like I said, normally this is existing buildings and you've putting a new building online. So that way it's a little bit of a bigger problem. It's a bigger problem if you don't have enough flow and you have to manage these other buildings down to get flow. Once done upon the block balance valves, open the block balance valves, and just like you do a regular system, there's no difference there. Record the building balance flow and balance valve set point. Record system differential pressure set point. So your job is, if you're just doing one building, then you'll set up all this building, set this set point where it needs to be. But you may have to reset up the system set pressure if you need more pressure to run this whole system. Now, the third one is the one you will normally see, which is a campus variable primary tertiary pumps. So in these here, we have a pump that actually pumps the water through the system and manages that differential pressure. And then we have a bypass valve, a temperature mixing valve, that sets the temperature for the building. So basically then we have, every building has a tertiary pump. Now, by the way, you can't mix between these systems. If one building's got a tertiary pump, they all should have tertiary pumps. Mixing will be a complicated nightmare. I haven't ever run into a mixed one, but I've run into problems with the previous one, which just had the valves. I've had problems with that one. This one, the general problem is just not having enough pressure. But basically, each of these buildings stands on its own, and then when it gets, if this pump is full flow and it can't reach its set point, then it calls for this set point to go up. So it sends a signal to the central plant, I need more water. If the temperature is in full open to this valve and it still can't satisfy, then it sends a signal to lower the temperature because it needs colder water. So control of a primary tertiary pump system. So remember, again, the buildings are like they would be normally. You don't have to worry about that any differently. And then the central plant's the same as a central plant. The primary secondary pump P1 is the lead pump, and P2 is a lag standby pump. That's these up here. The lead pump VFD should modulate to maintain this set point. If the primary secondary pump system differential pressure drops more than 2 psi for 15 minutes, then we're going to change pumps. And that can have a different sequence, but that's just a simple sequence to do there. Each building tertiary pump speed modulates to maintain the building differential pressure control set point established during the system flow balance. Send a low pressure signal to the primary pumping system to increase main pressure when pressure drops below set point and the pump speed is at maximum. So if this pump doesn't have enough water, it's going to send a signal saying, I need more water. The building three-way temperature mixing valve bypasses flow to increase the building to water supply temperature between minimum and maximum, 42 to 56, based upon the desired temperature difference in the system. Send a high temperature signal to the central plant to lower the chill water temperature when set point cannot be achieved. That's pretty simple systems on how to run them back and forth. Each building chill water supply temperature set point is set by the building load and humidity requirements, and it is reset based upon the coil valve position, just like other systems. So let's look at balancing one of these systems. Test and balance procedure for the central plant is the same, and for the building are the same, just like the other systems we talked about here. So those are all standard. We don't have to worry about those. Those are explained elsewhere. Lock each building three-way tertiary valve for 100% flow back to the main return. So basically, we're locking it so it goes through the system. Set up the campus system for total flow diversity, if any, by blocking the associated percentage flow to one building, then balancing each building flow by adjusting the building balance valve. And then when you're done with that, you go back and close those, open those valves and close the other. So now you put them all balanced. So you're balancing the balance valve there at the building, because we're assuming the building's already balanced. So the beauty about a tertiary system is you don't have to go screw up the other buildings. You can leave them balanced. You're only dealing with right there at the center, at what's entering the building as a tertiary pump. So that's good. To balance a flow to each building in the campus system, override each building temperature three-way valve to full flow to the bypass and balance the building balance valves. So you're doing the same thing. You're taking all this different pressurization downstream. You don't care about it because you're just doing the upstream side. The tertiary pump system works really well. A lot of guys don't like it, operators, because they got another pump running, but if you're designed correctly, it doesn't really add much horsepower. Return the tempering valves to fully auto control, and of course the pump to full speed control. Record each building balance flow and balance valve set point. Record system differential pressure set point. So campus systems look big and scary, but really they're pretty simple. So VAV wasn't too difficult. I hope that was beneficial. If you have more, or if you need more information, please go see the other sections, T20 and T7. It'll help you do that. Again, thanks a lot for watching. I really appreciate it. Thanks for being a subscribing member. You're really helping me, and I do appreciate that. Have a great day, and I'll catch you on the next one.